Hi there. We are finishing off Chapter 2 this morning. We're going to do sections 11 and 12, and we are talking about the concept of buoyancy. So when we talk about buoyancy, what we find is that if an object can be either fully or partially submerged in a fluid, and that whether it's fully or partially submerged in a fluid depends on the nature of the object itself and also the specific weight of the fluid that it is submerged in. So some examples of full submersion might be a hot air balloon. Well, it's kind of a strange thought, but a hot air balloon is fully submerged in the surrounding air. And the reason that it floats upward is that there is a buoyant force due to the fact that the hot air inside of the air balloon has less density or less specific weight than the cooler air outside of the room, or outside of the balloon. So that's why the hot air has to stay hot, and there will be burners or whatever in order to keep that air hot. But the hot air actually is less dense than the air surrounding it. Some other examples of full or partial submersion would be an iceberg floating in the ocean. And you've heard the expression tip of the iceberg, meaning that generally speaking, I believe about 10% of the volume of the iceberg actually floats above the water. And then there are other objects. For example, if you have a bathtub and you have a bar, here's your water in the bathtub, and you have a bar of soap, the soap will float or partially float or sink depending on the density of that particular bar of soap. And legend has it that this is actually how the principle of buoyancy was discovered. Back in ancient times, there was a scientist named Archimedes, and this is referred to as Archimedes Principle. And Archimedes Principle, which is stated in the first part of section 2.11, says that when a stationary body is completely submerged in a fluid or floating so that it is only partially submerged, the resulting fluid force acting on the body is called the buoyant force. And it turns out that the force of buoyancy is always directed vertically upward, but it is equal to the submerged volume of the object times the specific weight, not of the object, but of the fluid that the object is submerged or partially submerged in. So in other words, if you think about the volume, the submerged volume of the object, whether it's partially submerged, as in these cases, or fully submerged, as in this case, what's really happening is the submerged volume is the amount of the fluid that's been displaced by that object. So if you take the submerged volume of the object, that's really equal to the volume of the fluid that has been displaced times gamma of the fluid gives you the force of the fluid acting on the object, okay? And if it's sitting still, those forces are all going to be normal forces, but it's always going to be equal to this. So if you look at an object that's floating, you have the buoyant force acting up, and you still have the weight of the object acting down. And when stability is reached, in other words, where it is not rising or sinking, stability occurs when the buoyant force is equal to the weight of the object. Okay, so to finish off this little discussion then, we know that the buoyant force is equal to the submerged volume of the object multiplied by gamma of the fluid, specific weight of the fluid, and the weight is what the weight has always been, whether it's partially submerged or fully submerged, the weight is still the same, which is the volume of the object, not just the submerged volume in the case of a partially submerged object, but the entire volume of the object times the specific weight, not of the fluid, but of the object. And this determines how something floats. All right, so on page 75 of your textbook, Archimedes' principle is stated in the blue box on the left-hand side. The buoyant force has a magnitude equal to the weight of the fluid displaced by the body and is directed vertically upward. So let's talk about a couple of consequences for this in the real world. What do you know about saltwater versus freshwater? Well, freshwater, the gamma of freshwater, is less than gamma of saltwater because saltwater has, of course, salts, NaCl and other salts dissolved in it. So this gamma is greater. So if you take any particular object, let's put it in a vat of salt water, and let's put it in a vat of fresh water. We take our same object. Let's just put a ball. Okay? The weight of the ball remains the same in both cases, doesn't it? But the buoyant force here is equal to gamma of the salt water times the volume submerged. And here it's equal to gamma of the fresh water times the volume submerged, whether it's partially or fully submerged. But what does that tell you? It says that since gamma of the salt water, these two are the same, so if we say the buoyant force minus the weight is going to equal 0 at stability, if this is greater for the salt water, the weight remains the same. What does that tell you? Well, it's going to float more. It may even pop out of the water. And so the natural consequence of this is objects float better in salt water. Objects that would sink in fresh water will sometimes float in salt water. There's a consequence for this for swimming as well. Swimming in the ocean, or if any of you have ever swum in a salt lake, like Salt Lake City, Utah, it's very much easier to swim. Human body composition is for a thin person, because muscle and bone weighs more than fat, but body composition or body density for a very thin person tends to be close to the density of fresh water. It's not exactly the same. It's always a little bit different, so that most everybody can float in fresh water, but most everybody can float very, very well in salt water. And once in a while you will get somebody who's a sinker. They tend to be extremely thin, athletic men, or little kids, scrawny little kids, can also be sinkers. So that just has to do with the relative density of their bodies. But almost nobody will sink in salt water. All right, so there's a couple of other consequences of buoyancy. And one of the consequences of buoyancy is that objects can tend to be more or less stable, depending on what is called the center of buoyancy, compared to the center of gravity. So the geometrical relationship between those two things will determine whether something is stable or not. Now, in general, if you look at ocean seafaring ships, this is my idea of a cross-section of what a ship looks like. They tend to be quite deep in the water, and that depth makes them more stable. It also has to do with another thing is that heavy cargo tends to be loaded low in the hull, and that promotes stability as well. If you have a ship, and an example of this are ships that trade merchandise or that carry freight on the Great Lakes, Lake Michigan, what is it? HOMES. Huron, Ontario, Michigan, Erie, Superior. Big trade routes in the Midwest. Even though the lakes are very, very huge, they're not anywhere near as huge as the ocean. They have miles and miles of shoreline. So the boats in the Great Lakes tend to have low, flat hulls. And for that reason, they're less stable than ocean-going ships. But these types of ships are not effective in the Great Lakes because of the shoreline. The shorelines tend to go very slopey rather than dropping off very quickly. And also just the basic depth of the Great Lakes is not anything near compared to the oceans. So we tend to have a shallow-hulled ship and less stability. But mathematically, what does that stability look like? Well, basically, the buoyant force acts from the center of buoyancy. And the center of buoyancy is the geometric center, in other words, the areal center of the submerged area. Right. So if you have the entire thing submerged, it's going to be in the geometric center of the entire thing. But if you only have 3/4 of it submerged, the center of buoyancy is at the center of that area. Whereas the center of weight, or the center of gravity, acts from, well, if the weight is evenly distributed, it will be the centroid, or you can move it downward by loading it heavily toward the bottom. So basically, the application of this, or the thing to watch out for, is the relationship between the buoyant force, the moment created by the buoyant force, and the moment created by the weight will either create a righting moment, meaning that if it tips, it will tend to right itself, like here, where the buoyant force is here. If it tips, the buoyant force moves this way, but that the couple produced by those two forces tends to correct itself and send the ship, or whatever the object is, back to a stable configuration. If the weight, however, if the center of weight or the center of gravity is above the center of buoyancy, what happens in this case if it tips is that the moment will tend to overturn it, continuing that tipping, and will actually overtip the ship. So this is a bad, unstable situation, and this is a good stable situation. So the quickest way to avoid this happening is to create most of your weight down below, which will lower the center of gravity and hopefully keep it below the center of buoyancy. You can have stability with the center of weight above the center of buoyancy if, well, it's a little bit interesting. They can't be collinear, so you have to have certain loading configurations, but having it so that the buoyant force is above, the center of buoyancy is above the center of weight always creates a righting moment. If it's backward, then you have to do some fancy math to make sure that you have some sort of stability. Now, there are other types. You can be really stable, fully stable, you can be partially stable or unstable, and that all depends on the relationship between the size and the magnitude of those moments. All right, so the last thing I would like to do today for buoyancy is to work a problem for you that demonstrates the idea of buoyancy. And the problem is 2.84, and I titled this the swamp logger problem. This is a real world problem from 20 years ago, or maybe longer than 20 years ago. But it has an application. I thought it was an interesting problem based on the fact that this scavenger operation is actually happening in today's world. So problem 84 says that when the Truncated Dam was constructed in northern Brazil, the lake that was created covered a large forest of valuable hardwood trees. It was found that even after 15 years underwater, the trees were perfectly preserved and underwater logging was started. During the logging process, a tree is selected, trimmed, and anchored with ropes to prevent it from shooting to the surface like a missile when cut. Why would it shoot to the surface? Well, because the buoyant force. What it really is saying is, this is a geographic or geometric representation of a tree, is when you remove it from being tangled up, when you trim the tree, cut off the branches and untangle it from what else it's tangled in, when you cut the tree off, what happens is the buoyant force tends to project it toward the surface of the water while the weight pulls it down. But the buoyant force is greater than the weight, meaning that the density of the tree is less than the density of water, or the specific weight of those two things. And so you have to restrain it by making sure that you tether it with ropes that exert a vertical component of force that will, along with the weight of the tree, offset the buoyant force. Okay, so the specifics said, assume that a typical large tree can be approximated as a truncated cone with a base diameter of 8 feet, a top diameter of 2 feet, and a height of 100 feet. So I've drawn that here. We have a diameter at the base of 8 feet, a diameter at the top of 2 feet, and a height of 100 feet. And that's a lot of board feet of lumber as well, isn't it? That's a pretty big tree. Determine the resultant vertical force that the ropes must resist when the completely submerged tree is cut. The specific gravity of the wood is approximately 0.6. So what we have then is how much vertical or downward force must the ropes exert. So the basic principle goes back to statics. The summation of the vertical forces have to equal 0, because if they're not equal to 0, there will be an acceleration. And if the buoyant force exceeds the tension, the vertical piece of the tension, and the weight, then the acceleration will be upward. So what I've written is assuming, or not really assuming, but using my sign convention as this being down, whether we call this the z direction or whatever, this is negative z. So we're going towards 0 and we're going up. That means that the tension in the ropes, the vertical component, is going to be pulling down, so it's negative. The weight also will be acting downward, and the buoyant force will be acting up. In order for stability to occur, in order for it not to shoot up, we need to have those things equal to 0. So I rewrite that the buoyant force minus the weight equals the tension. Or another way to think about it is, if you put weight over here, you would get weight plus tension equals the buoyant force, meaning that the buoyant force has to be offset by the weight of the tree and the tension in the ropes. All right, so continuing with that, what's the volume of a truncated cone? I did not have this at my command. I had to go to Purple Math or some other source to find out the volume of the cone, maybe my CRC math tables. Turns out that if you know the upper radius and the lower radius of a truncated cone, it's this expanded term multiplied by pi times h over 3. So I went ahead and did the math, and I found the volume of the tree is 2,198 feet. Okay, so what does that mean for my tensions and my weight? Well, the tension is going to equal the buoyant force, which I know is the volume submerged times gamma of the fluid, which it says this is a lake, so we can assume that that is fresh water. And this would be the buoyant force minus the volume submerged times gamma of the tree. Okay, and that's going to equal my tension. Getting another piece of paper here. All right, so the volume submerged, the entire tree is submerged, isn't it? After that, we're going to have less buoyant force, but while the tree is fully submerged is what we need to compensate for. So we have 2,198 cubic feet of the tree submerged times gamma of the fluid, which is in English units, 62.4 pounds of force per cubic feet. That's on the inside front cover of your book, minus the volume submerged, which, since it's fully submerged, is exactly the same, times the gamma of the tree, which we're told has a specific gravity of 0.6. So that means this is 0.6 times 62.4 pounds of force per cubic feet. And that has to equal the tension. All right, so to simplify the math a little bit, I can see that I have this term and this term in both. So I can pull them out, 2198 times 62.4. Then I multiply that by, this is 1 minus 0.6, which turns out to be 0.4. And I can also see that I have cubic feet canceling cubic feet. So this is going to be in pounds of force. All right. So bringing out my calculator then, I have 2198 multiplied by the specific weight of water, 62.4, multiplied by 1 minus 0.6, which is 0.4, and my total value is a tension of 54,862 pounds of force. All right, so that means when I tether that tree, in order to prevent it from shooting up out of the water, we need to apply almost 55,000 pounds of force. Right, so that's it for Chapter 2. Your homework problems have been posted to Moodle. So after you watch this vodcast, you are ready to finish your homework, both for Chapters 1 and 2. Then call me or email me to arrange a problem solving and review session prior to the test. Then I will give you the test over Chapters 1 and 2. Thanks. Have a great day.